Good morning. So, in the last lecture, we had seen about the measurement of pressure and strain, and in the next two lecture, we would look into the various ways in which temperature can be measured. Okay, so for measurement of temperature, you have non-electrical methods. You have electrical methods of measurement, and for very high mm, uh, temperatures, you can even just measure the radiation that is coming out of that hot object to be an indicative of the temperature of the object. So, coming to the instruments that are being used, in case of non-electrical methods, basically the concept is that the expansion of a fluid is made as an indicator for the measurement of the temperature. So the fluid can either be a liquid, so that is a liquid in glass thermometer, and the medical thermometer that you usually see are fall in this category. They are liquid in glass thermometers, where mercury is a liquid that expands in a glass enclosure. You also have bimetallic thermometers, which in which case use uh, um, take advantage of a differential expansion of two metals and to indicate the temperature variation. And in case of a pressure thermometer, we know that as pressure increases, the volume occupied so as temperature increases, the volume occupied by a gas will increase, and thus if the gas is confined in an enclosed space, the pressure that is exerted by that gas is going to is going to be dependent on the temperature, and that concept is used in a pressure thermometer. So these are the non-electrical methods for temperature measurements. And coming to the electrical methods, you either use, like the case of a strain gauge, we use the in thermoresistive um, transducer, you make use of a resistance change of certain materials with temperature. So in case that material is a metal, uh, we have RTDs, resistance temperature detectors, whereas the temperature increases, the resistance also increases. Or you also have thermistors, which are semiconductor based temperature transducers, where the temperature decreases, where the resistance decreases as the temperature increases. Okay, then these are thermoresistive, and you can also use the thermoelectric principle, which states that if two dissimilar metals have two ends kept at different temperatures, then there is a potential difference that can be experienced across these two ends, and there is an electric potential generated across the temperature gradient, and that is made use in a thermocouple. Okay, and in case of really high temperatures, the radiation can be used. The radiation being produced by this hot object is being the dominant wavelength of that radiation is used as an indicator of the temperature, and that concept is used in pyrometers. So in this particular lecture, we would look into these non-electrical methods of temperature measurement, and in the electrical methods, we will look into the thermoresistive kind of temperature measurement. So as I mentioned earlier, in case of non-electrical temperature measurement, the temperature is indicated by the change in the physical state or physical properties of some material. Okay, and in case of a bimetallic thermometer, what is happening is that you have a cantilever made of two metals, Okay, they are sandwiched together, and and in this bimetal cantilever, when the cantilever is subject to heating, okay, so then both the metals will expand, and however one of them expands at a faster rate than the other, so then there is a bending that is happening. Okay, and the amount of bending is indicative of the difference in temperature from the temperature. So if let us say there is a temperature T0 at which it is the nominal temperature at which the beam is straight, and a temperature T1, then at T0 it is a flat one, at T1 it is bent, and the amount of bending is indicative of T1 minus T0. Okay, the temperature range that can be measured by using this bimetallic thermometer is quite large, in the range of -30 to 500 degrees centigrade, and this doesn't require an external power source, so it's a self-generating instrument. However, the problem is that since it's a metal and it has to be heated, the response time is quite slow, and hence rapid change in temperature can't really be measured using a bimetallic thermometer. Okay, and to increase the sensitivity, usually what is done is that a helical structure, the bimetallic strip is put in a helical shape, and therefore whatever may be the differential expansion, that is sort of enhanced, and that will have a better sensitivity. Let's go a bit into the mathematics of this. Let us say that after the bimetallic cantilever is bent, okay, it bends into a shape with a radius of curvature of rho. So this radius of curvature rho is related to all the parameters of this strip, namely the total strip thickness, the ratio of the modulus of elasticity of these two materials, okay, the ratio of thickness of these two materials, and the coefficient of thermal expansion of both materials, okay, and the differential temperature. So all of these things are related to the radius of curvature using this uh, relationship. And note that it's not necessary that T2 is greater than T1. So for example, if T2 is greater than T1, and if you assume that the material A expands more than material B, then if T2 is greater than T1, you would have a shape that comes like this. And when T2 is less than T1, conversely, you would have the material A contracting more than material B. So you would effectively have rho being negative in this case, and here rho is positive. Okay, so now, but to make this matters simple, what is generally used is that you use a material in which whose elastic modulus ratio is almost the same, and you use similar thickness for A and B. So Ta by Tb by Ta will also be equal to 1. Okay, so from this this will simplify it to a relationship like rho being basically inversely proportional to T2 minus T1. And now in this equation, T and alpha A minus alpha B, they are all constants. So what you have is rho is proportional to 1 by T2 minus T1, is directly. However, now this inverse relationship is not going to be really useful, but and the other point is that we can't really measure the radius of curvature. What you can really measure is only the deviation that you have from the what do you call, from a flat strip. Okay, the amount of deviation that you get, and this deviation is again inversely proportional to rho. Okay, if the, of course, if the deviation is not too large, okay, the deviation is going to be inversely proportional to 1 by rho. So which would mean that this deviation is directly proportional to the change of temperature, and this can be used as an indicator to calibrate the dial. Rather than rho, we will calibrate the dial based on the deflection, or based on the deviation d, and deflection or deviation, and that can be calibrated to indicate the difference in temperature. However, this would require us to know what is T1. Okay, the temperature at which the bimetallic strip is flat, that knowledge is necessary, or else what you are basically looking at is only a measurement of T2 minus T1. Next, we have the liquid in glass thermometer. This is the most commonly used and the most familiar thermometer that you have. So you can have, you do have the mercury thermometer, which are basically used for measurement of body temperature, and for in laboratories you also have the alcohol thermometer, which is used to measure room temperature or temperature of certain liquids. Okay. However, one basic disadvantage, the advantage that you have here is that the liquids are can expand much more than solids. Okay, liquids expand much more than solids, so which would mean that the liquid in glass thermometer can be made much more sensitive than the bimetallic thermometer. And on top of that, if the expansion of the liquid is made in a capillary of a very small radius, then the indication, the linear expansion that you have in the capillary is going to help the sensitivity and make the apparent sensitivity of the liquid in glass thermometer to be quite large. However, we have seen that due to the metals being solid at a very large range, so metals, as we have seen in the bimetallic case, bimetallic thermometer can measure up to 500 degrees centigrade. Okay, and that is because the metals remain solid up to 500 degrees centigrade. Okay. However, in case of liquids, the material is going to be liquid only between its melting point and boiling point. So they have a very small range of temperature measurement also. Okay, so that is the disadvantage that you have of liquid in glass thermometer. That is, the compared to other thermometers, the range is smaller. However, sensitivity can be made large. Okay. The other disadvantage that you have is, the advantage is that in addition to being quite sensitive, they are low cost, simple, and also portable. They are not as bulky as the other types of thermometers. However, since the presence of glass in the assembly, there is a fragility in the instrument. And in addition, since they are basically an indicating instrument, which are also non-electrical in nature, and then this would mean that they are really not useful for remote indication. You have to be present at the place where the thermometer is located. Okay, and the heat being transmitted is through this bulb, so the heat capacity of the bulb plays a really important role in the functioning of the thermometer, in the response time of the thermometer, essentially. So if this bulb has a high heat capacity, so either the bulb has a metallic coating for better heat transmission, okay, or the volume of the bulb is larger, so for greater sensitivity. So this would mean that it will take time for the bulb to heat up. and then transmit the reading as an indication here, and then the liquid to expand and so on. So which would mean that the it would take time for the thermometer to give a suitable indication, and this is quite understandable because and this is the reason why whenever you are using a mercury thermometer to measure temperature, you can't just get an instantaneous reading as you usually get in a digital thermometer. Okay, so in a market, so which would mean that, and that is the time period of the thermometer being taken. Okay. Moving ahead, we also have a gas-based pressure thermometer. So in this case, you use the expansion of a fluid, basically a liquid or a gas, along a pressure measuring device like the Bourdon tube. So you have a sensing bulb here that is connected to the pressure measuring device using a capillary. Okay, so when the fluid in this bulb is heated, it expands and fills this Bourdon tube, and because the pressure in the Bourdon tube is increasing, an indication is given. And because there is a possibility to use a gas, again the range of operation is again of the pressure thermometer is also high. Okay, so it can measure temperatures from less than 0 degree to up to 500 degrees centigrade. And however, because of the presence of this sensing bulb, okay, the heat capacity of the sensing bulb also comes into picture, and hence the response can be slow. Okay, because gases do not respond so accurately, and so at higher temperature the sensitivity is lower, then the sensitivity of this gas thermometer is not as good as the other thermometers. Gas based pressure thermometers are not as good. Okay, however, there is one advantage of these thermometers, that is that you can have a long capillary tube. So this indication, okay, this dial can be at a location that is reasonably far away from the site, from the site at which the temperature is being measured. So you can have the remote terminal, the terminal at which the temperature is being measured here, and the dial being kept here. This was not an option in case of a liquid in gas thermometer, where you have to go to that remote location to measure the temperature. So this was the non-electrical temperature transducer. Moving on to the electrical transducer, the first one that we'll see is a resistance temperature detector. So as the temperature of a material changes, the resistive capacity of it also changes. So if you have a material whose resistance is R0, as at a temperature say at a temperature T0, okay, so at a temperature of T plus T0, the resistance can be given by can be approximated by a polynomial equation. Okay, so as the temperature range increases, the equation tends to deviate from a linear relationship. Okay. So even though we would like to have R is equal to R0 plus into 1 plus alpha t, in reality this relationship doesn't hold when as t the value of t increases to a larger value. Okay, so in reality what is being approximated is as a polynomial equation. So if this is done and the temperature versus so R by R0 versus temperature graph is plotted, what you tend to see with different materials is these different graphs. Okay, you can see that from this graph that platinum has the most linear looking characteristics. Okay, and over a wider range. Nickel also looks linear, but the range is not, the range is restricted. Okay, copper is cheap. Okay, but it deviates from linearity as the temperature increases. Okay, tungsten, the resistance doesn't increase so much, okay, with temperature, and also it is not as linear as platinum. So what we see is that a platinum has the most linear characteristics. In addition, due to its chemical property, it is also corrosion resistance. Okay, however, it is also costly. Okay, on the other hand, as I said earlier, copper and nickel are more linear and susceptible to corrosion. Okay, however, they are cheaper options. So depending upon your application, with how much you value accuracy and linearity, you can go for whichever uh, RTD that is to be used. However, in most cases, platinum is the preferred choice for an RTD material, even though it is costly. And typically, the R0 value, when taken at, say, a temperature of 25 degrees, okay, is given as 100 to 1000 ohms. So you have a choice of 100 to 1000 ohms. But even though it is depending upon specific application, you can have the base resistance being either lower or higher value. Okay, so basically you have the RTD wire being kept in a housing. Okay, and the leads lead to the other parts of the circuitry, and by connecting it to an appropriate circuit, we are measuring the resistance, and from the resistance we'll try to figure out what the temperature is. Okay, so coming to the basic construction of the RTD, so there is a temperature sensitive wire here. Okay, this is being wound around a hollow former. Okay, and the leads are taken out. Okay, and for better protection, you would have this entire assembly, the resistance element, being covered in a protective cement. Okay, in certain cases, and this entire assembly is housed in a sheath. It can be metallic sheath or it can be of other material. Okay, and the purpose of this thing is that when you have this cement, okay, it protects this wire from mechanical stresses, and this metal sheath protects it, makes it possible to use the RTD both in electrically conductive or in corrosive environment also. Okay, so if for example you are trying to measure the temperature of a corrosive liquid, then the presence of this cement and the sheath is going to help in it. However, the downside of this is that the sensitivity is definitely reduced, because this entire assembly, the cement and the metal sheath, have also to be heated up. Okay, so sensitivity of the RTD decreases it is kept when it is used with the metal sheath and the protective cement housing. Okay, however, if it is sure that the environment in which the RTD is being used is non-corrosive and non-electrical, okay, not conducting electrically, or not electrically conductive. Okay, then we can forego this housing and directly have this RTD being exposed to the temperature source, and in that case the sensitivity can be enhanced. Typically RTDs are used for measurement of temperature at remote location, okay, which would mean that the leads have to be longer, okay. And so if you have an RTD here, okay, let us say this is RT, and you have a long lead, the lead resistance RL also plays a part, okay. And for this purpose it becomes necessary to compensate for this lead resistance in the way the RTD is constructed itself. So typically what you have is RTDs in which you can either have 3 lead RTDs or 4 lead RTDs. So in case of a 3 lead RTD, you have 2 leads, or you have 3 leads, all of the same length, all from the same material, so that their their lengths are same, the material is same, so the resistance of all the 3 leads are going to be the same, and 2 of those leads are connected to one side of the RTD and the third one is connected to the other side of the RTD. As it can be seen here, these 2 are connected to one side and this is connected to the other side of the RTD. Okay, coming to how this 3 lead wire RTD can be used. Okay, this is a circuit diode. A Wheatstone like bridge is used for it, a modified Wheatstone bridge. This setup is called as a double slide wire bridge. Okay, so you have the RTD being connected, and these are the 3 leads of the RTD. 2 of them are here and one is here, whose resistance is RL. Okay, and they are connected in this double slide wire bridge, in which there are 2 variable resistance S2 and S1, and the sliders of these 2 variable resistance are coupled together in a manner such that at any point of time the proportion of S2 being coupled to be in series with this R3 is the same as the proportion of S1 coupled to be in series with R2. Okay, and now let us see that how that helps in the measurement. Okay, so let me again write, this is R3 and here there is an RL. Now by appropriate motion the bridge is balanced. Then at balance what you would have is RT plus RL divided by RL plus R3 plus F times S2 is the same as R1 plus 1 minus F times S2 divided by 1 minus F times S, so 1 minus F times S1 here, and divided by 1 minus F times S2 plus R2 plus F times S1. Okay, now you see that if you know F, then you can say that you can, if you know F and since all the other resistances are known, then what can be done is that you can really calculate it. However, if by chance the right hand side can be made into unity for all values of F, okay, then the equation simplifies much more, and I can get RT to be R3 plus F times S2. I need not worry about what are the values of R1 and R2 or S1. Okay, so that need not be the users need not have that information at all. The actual values of R1 and R2 and S1 need not be known. What I only need is R3 and S2, However, for that to happen, this one is equal to 1 for all values of f. That should be possible. Let's see if that is possible at all. Okay. So for all f, you should have this equation to be satisfied, with which, when simplified, turns out to be that the choice with a of S1 being equal to R1 minus R2 and R1 minus R2 being half of S2. Okay, so with this choice of S1 and S2, R1 and R2, you can make the right hand side being equivalent to unity, and which would mean that by merely measuring F, okay, by merely measuring the slide wire position, I can basically get a value of the resistance. Okay, in fact, the slide wire itself can be calibrated in terms of RT, because R3 is going to be constant and S2 is going to be constant. On the other hand, if we had not done that, then in each reading, at each balance, you have to solve this equation for RT. Okay, hope that is clear. So in certain application, it may be needed that you need a much more accurate measurement of the temperature. Okay, in such cases, you, instead of using a 3-lead RTD, you use a 4-lead RTD. And the construction of this RTD is very similar to the construction of a 4-lead low resistance resistor. Okay, so you would have current leads and you would have voltage leads. Okay, so these current leads are of low resistance and the voltage leads here are of high resistance. So here you have an RT, you have two voltage leads T and C, okay, small t and small c, and two current resistors, capital T and capital C. Okay, so you have two capital T and capital C are low resistance leads, and small t and small c are the high resistance leads. Okay, and as in the case of the low resistance measurement, the high resistance lead are connected to the supply. Okay, and the low resistance leads are always connected to the other parts of the bridge circuit. In this case, you would notice that only 3 of the 4 leads are being used. So one of the high resistance leads is left out, and so the measurement is done with 2 configurations, and the reading is taken as RT is the average of these 2 measurements. Okay, and now if you have R1 equal to R2, then let us see what is happening here. Okay, if R1 is equal to R2, then at the balance you have this one. Okay, so in one of the configuration, RT plus T is the same as R3 1 plus C. Let us say this is the balance is at R31 here. Okay, similarly the balance here is at R32. So in this case, R3 plus T is R1 plus C. Notice here we are not saying, in case of a 3-lead, we had assumed that all the leads are of the same resistance. Here we don't make that assumption. We only say that capital T and capital C are low resistance and small t and small c are high resistance. Okay, we are not making any assumptions on the specific values of these resistances, the lead resistances. Hence, we are since we are not making that assumption, we can expect higher accuracy in that case. Okay, so here which would mean that when you average both these values, R31 plus R32, you basically get the value of the resistance of the RTD. Okay, now you have this RTD. When you look at this entire assembly, okay, with these 4 leads, okay, they are available at the uh, control room. Okay, similarly, these 4 leads are again available at the control room for connection. Okay, so basically the change in circuitry can be done at control room. So the change can be done at control room, okay, and not at remote terminal. That is what I say as RT. Okay, so you need not, so which would mean that all these changes can be done at control room without bothering to visit that location in at where the temperature is being whose temperature is to be measured. Okay, so that is another advantage here. Okay, and these 4-lead RTDs can also be used in digital thermometers, where you have the high resistance leads being connected to a voltmeter and the low resistance lead being connected to a constant current source. Okay, so now what is happening is that this voltmeter is measuring the voltage across the RTD. So what you have is RT is less than what you call RL1, okay, or RL2, and that is much less than the voltmeter resistance. So basically the voltage across the RTD is being measured because literally no current flows through this circuit. Okay, and that and from that you can get the RTD value, the value of the resistance to be V by I. But I is going to be constant. So this voltage measurement from the digital voltmeter is going to be a direct indication of the resistance. And since this resistance is again literally directly proportional to the temperature, this voltage is directly indicating the temperature. Okay, and that way you can use the 4-wire RTD to in digital thermometers to measure temperature. Okay, now listing out the salient features of an RTD, though mostly RTD resistances are confined to say 100 ohm to 1 kilo ohm, you can have RTD resistances ranging from 10 ohms to 25 kilo ohms also. Okay, and because they are basically metal based transducers, they can operate at a wide range of temperatures down from minus 260 degrees centigrade to as high as 1000 degrees centigrade. Okay, and over most of this range, the high degree of linearity, if you take the platinum RTD, high degree of linearity and high accuracy up to 0.1% can be achieved. Okay, so in case of platinum RTD, this 0.1% accuracy can be achieved in the range of say minus 50 to 500 degree centigrade. Okay, however, if the environment in which the RTD is working in that has moisture in it, there is humidity in it, that humidity can significantly affect the accuracy because water would have heat capacity and that itself will change the apparent temperature that the RTD is feeling. Okay, and the basic working principle of RTD is that temperature is converted to an equivalent change in resistance of the RTD. So the typical sensitivity of an RTD is of the order of 0.0038 ohms per ohm per degree centigrade. Okay, this is in most of the range, most of the linear range. Okay, now as we have seen in case of the RTDs, you can use sheathing when operating in, which will give protection when operating in conductive or corrosive environments. Okay. However, the shielding is going to reduce the speed of response, with the response speed even after that being less than 1 second. Okay. So next, after the RTDs, we will look into thermistors or thermal resistors. These are semiconductor resistors, and contrary to the case of RTD, the resistance of a thermistor decreases with temperature and is usually given by this nonlinear equation, where the factor beta is of the order of a few thousand, and T1 and T0, the base temperature and the are being measured in Kelvin. Okay, so as you see that when you plot this R by R0, you are going to get a highly nonlinear graph. Okay, so this R by R0 versus T is a highly nonlinear graph. However, which would mean that, and you would also see that there is no range at which it is linear. So of course you can take a very small range, okay, and say the graph is linear in this range, but this temperature range would be so small that it's impractical to use the thermistor as a direct measuring device. Okay, so the resistance of the thermistor can't be measured directly, and at least easily can be interpreted as a temperature without having a appropriate circuitry. Okay, so there are three options here. Okay, either you map T to R, okay, you measure R and use the nonlinear relationship to get T, so that you have a scale that is nonlinear, or you measure R, find log of R by R0, okay, and then from that map it to 1 by T. Okay, so that will be a linear relationship, and from this 1 by T you find what is T in degree Kelvin, of course. Okay, so that is the second option. The third option is to use linearizing circuits. Okay, so typically in mostly, instead of going through the hassle of either of the first two options, people tend to use linearizing circuits. Okay, so these are a few linearizing circuits. I'm not going to explain too much into this. What I'm going to say is that in this circuit, the resistance of this combination is being measured, and that is being correlated to the temperature. Okay, so basically as T2 increases, so this is in both of these cases T1 is constant. Okay, T1 is constant, and let us say T1 is 25 degrees centigrade for this thing. So as T2 increases, R decreases in this case. Okay, and in this case, as T2 increases, E0 increases, and E0 plus increases, and E0 minus decreases. Okay, basically as T2 increases, this combination is going to decrease in resistance, because you see that combination is the same as this one. Okay, this combination of resistance is going to decrease. Okay, which would mean that in the total resistance, this would have a higher proportion. R2 will have a higher proportion to this one, so which it is natural to assume that E0 will increase and E0 plus will increase and E0 minus will decrease. And the way these factors will decrease is more linear than the way R versus T relationship is. Okay, so some sort of linearity is being put in there. Okay, so as I said that in both, if you assume that both the thermistors here are of similar material, okay, and they at the temperatures T1 is RT1, then in the voltage mode we have E0 and E minus, they vary linearly, and with E0 increasing and E0 plus increasing and E0 minus decreasing with temperature, and in the resistance mode the overall combination of resistance decreasing with temperature. Okay, one major what do you call factor in the use of thermistors is that they should be used, or they should generally be operated in low current regimes, and this is because of their uh, temperature coefficient of resistance being negative, which would mean that if by chance the thermistor is operated at a range at which you have significant current flowing in such that the thermistor gets heated up, okay, the current is large enough to heat the thermistor. Now the heat is basically a temperature increase of the thermistor, and the thermistor's resistance decreases. Now if you are using a standard voltage source, okay, being connected to the thermistor, what is happening is that this resistor is at a higher temperature. Now due to the higher temperature the resistance decreases, and which would mean that the overall resistance of circuit decreases, and which would mean the current is increasing, and increase of current again is going to do the same loop, okay, until it comes to a point where the power dissipated by the thermistor, okay, as heat is the same as the supplied power. Okay, so there is a runaway heating effect. So to avoid this, the thermistor is generally used in a low current regime, okay, where at this current these currents are not going to cause significant heating effects of the thermistors. And in addition, if there is a self-heating mechanism that is present in the thermistor, the temperature indicator or the resistance of the thermistor is no longer a reliable indicator of the temperature. Okay, so in a high current scenario this problem can exist. However, the same self-heating effect makes the thermistor very sensitive to change in the rate of heat removal. Okay, so which would mean that you can keep thermistor to measure flow rates of flowing liquids. Okay, so it can be used for gas composition or flow measurement in those uh, scenarios, like in smoke detectors or something of that sort also. Okay, so now going further to the salient features of thermistors, because of their semiconductor nature, they can be made to be compact and rugged and inexpensive and have good stability. However, because of the same lower size, uh, which would mean that it will have a lower surface area as compared to you will have a lower surface areas, which means that the heat dissipation capability is also reduced, which would again mean that there is the chance of self-heating is also increased. Okay. However, the same low size also helps in the response time being really very small. So you can have thermistors heating up and giving the correct indication in a fraction of a second, okay, to a few minutes even. Okay, that depends upon the particular mass and the thermal capacity of the thermistor, detecting thermistor. Okay. And temperatures up to 400 degrees centigrade can be measured, and the lower limit of the temperature is basically of the measured temperature is basically limited by the um, ohm meter or the resistance measuring circuit, because note that at low temperature the thermistor has high resistance. So in order not to show an infinite resistance at low temperature, you need, so it only depends upon what is the upper limit of your resistance measuring circuit. Okay. See, though the lower temperature limit that can be measured depends upon the upper limit of the resistance measuring circuit in measuring resistance. Okay. And as you have seen earlier, the operating currents have to be kept low to avoid self-heating effect. And this low operating current also means that the current sensitivity is lower in case of thermistor, okay, as compared to an RTD, even though the response time is much quicker. Okay, so with that we come to the end of the lecture. So the, what do you call, the material for the temperature measurement is spread over many books. So you can look at chapter 29 in A.K. Sawhney, which is measurement of non-electrical quantities, and chapter 12, which is again a temperature measurement chapter in Nakran Chowdhury's book, okay, or chapter 14 in Alan Morris and Raza Langare's book on measurement instrumentation, or chapter 8 in Dublin. Okay. So I have taken material from all these books, and you can look at these books for your reference. Okay. That come to the end. Thank you for your patience.